So now we see the advantage of cypherblock chaining. And the next thing I want to show you is the disadvantage of cypherblock chaining. So we talked before about how this works. The ciphertext coming out of each encrypted block is used as the initialization vector for the next block. The problem is, consider if you encrypt 47 bytes only, so you don't quite fill the last block. Now you have to add padding. You have to have a system of adding this padding somehow. And there is a system that is commonly used called PKCS number 7. And the way this works is if you only need 1 byte of padding, use a binary 1. If you have 2 bytes, use 2 bytes, each containing 2, 3 bytes containing 3. If no padding is needed at all, add an entire block of 16 characters. Now, the reason you would do this instead of just padding it with zeros or something is because it'll be easy to remove the padding when you decrypt it. You decrypt it, then you look at the last byte and you discard that many characters. That's the algorithm. That's the plan. The problem is this also creates a weakness, which we're going to see. So we're going to encrypt 47 bytes, and there's an extra byte there that's going to be padding. And all right, now suppose you do this. If you look at the decryption algorithm, this is where you begin to see the weakness. In the encryption, you took each block of ciphertext and used it as the initialization vector here to XOR with the plain text before encrypting it with the key. But decryption goes the other way. To decrypt, you take ciphertext, you decrypt it with the key, and then you XOR it with the initialization vector. And as a next block, you decrypt it with the key and XOR it with the input of this block. The problem is the attacker, who can see only the ciphertext and they don't know the key, can see the ciphertext. So I can see this text, and you're going to combine it with just a simple XOR operation here. That creates a fatal flaw. Here's the issue. Suppose I have 3 bytes of ciphertext and I'm trying to decrypt them, but I change this 1 byte here. If I change that 1 byte, this entire block will be scrambled to something random, and just this 1 byte here will change, because the only impact of this block of ciphertext on the next block of ciphertext is by this simple XOR operation. And if I change only this byte, it will change only that byte. That creates a weakness. Combined with the other issue that I brought up before, that this byte at the end is always a padding byte. So I can pretty much guess what that byte is going to be. So let's get this going. I've got PyCryptoDome. I'm going to have some initial values with a key and an initialization vector and some text to encrypt here to get going. So there we go. That's going to encrypt something. All right, I don't think it's going to print anything out yet. We'll see. Anyway, all right, there it goes. Module. Okay. I'm going to, because I made a new book, I need to install this library again. Wonder if I can add a block up here. I can. That's nice. Exclamation point, install PyCryptoDome. All right. There you go. All right. Now this should run. Okay, and it runs. Okay. So that sets the initial values. Now we're going to encrypt that text, which is just hello from AES. Okay, so it creates some long encrypted stuff, starting with F2. And now we're going to decrypt it. That created ciphertext. We're going to decrypt it and print out the results. Somewhere in here, I should be able to make a new block of code. There we go. All right. All right, so there it is in hex and in ASCII, and it was able to remove any padding at the end. All right, so now we're going to do padding and chaining. All right, so we're going to get ready. There's a simple sentence that's 47 bytes long. Okay. And now we are going to pad it and encrypt it. So we're going to add 1 byte of 1 to the end to pad it, and then encrypt it. And I'm wondering what the mod is. It makes a modified ciphertext string named mod, and then I'm going to make 2 of them. I'm going to make ciphertext, which is the original ciphertext with a byte of 1 at the end, and I'm going to make another one with this 1 byte modified. Byte number 31, I think is what that is. Yeah, I modified byte number 31 to change it into 255. So we can see the comparison there. So here's the 2 ciphertexts. I'm sort of confused why it ends in a 3. Okay, it does end in a 3, which is a little strange. I thought it would have a 1. Oh, it's encrypted. Okay, fine. So, right. So this is ciphertext, which is just random stuff. And now I've changed 1 byte at 32. I've changed this 5C right here. I've changed it to an FF. So these are 2 ciphertexts. This ciphertext here is the real encrypted message. And this is the modified encrypted message with 1 byte changed. So now when we decrypt it, we're going to decrypt the ciphertext and we're going to decrypt the modified ciphertext and print out the results. All right, and now you see the first byte block is identical. The second block is all destroyed. 65, 56 changes to 70, 96. All this stuff is scrambled into random garbage, but around here it starts getting good again. The third block is okay, exactly the same, but the last byte has changed from 01 to A2. This is a fundamental flaw in all cryptography. If you can do a manipulation that affects only part of the output, then that's almost always a weakness you can exploit, and so it is here. So by sacrificing an entire block of data in the middle, I was able to gain control over the last byte there. And that's the padding oracle attack. So we're going to make a vulnerable system. I wonder if I can figure out how to do this in this environment. I think the way to do it is make a text file here and upload it. So let me try that. All right, there's a text file. I'm going to save it as pador.py in the downloads folder. All right, and what this is just a library that's going to encrypt things with an IV and a key, and it's going to tell you whether there was a padding error when it decrypted it or not. And let me point out the result here. When this stuff is decrypted, the first one has valid padding here. 1 byte of extra padding at the end in a 0-1. The second one has a forbidden character at the end. Remember, the only legal padding bytes are 0-1 through 16. And this is A2, which is bigger. So this second one has a failure. It won't decrypt properly because the padding at the end is forbidden. And the fundamental weakness is if the system tells you that there is a padding error, that gives you enough information to deduce information about the key. And that's the game. So if I upload that padding oracle to here, then I can load that library from the local system. And there it is, pador. Okay. All right. Now I should be able to import the padding oracle and try encrypting a 47-byte sentence. And okay, it did in fact encrypt it and work fine. So the library is working, and I should be able to decrypt it. And I think I'm just going to talk about it from this point on instead of demonstrating it live, because we've done all the parts that are difficult. Now we got, okay, this sentence, here's the decryption. This simple sentence is 47 bytes long, and it has a byte of 1 at the end. That's the padding byte, which I didn't remove. You can see it here. So now that's the vulnerability. And so the problem is here. Here's what you're going to do. You modify this byte. and you're going to see if it creates you're going to try all 256 values of this byte, and you're going to find that most of them are going to fail, but there are two of them that are going to succeed. One is if you don't put it back to its original value, then you'll get the original message with its padding, and the other one that is not rejected will be the one that puts a byte of 0, 1 here, 1 byte of padding. I hope that makes sense. Since you know the pattern of padding, and you know this system where I can change 1 byte at a time right at the end, I can deduce this value here, this intermediate value, the decryption of this text. And after I know that byte, I can do it to the next byte and the next byte, and I can eventually deduce this entire orange block. And what that means is, even though I don't know the key, I can forge any message I want here because I know this block, I control this block, and I can combine them to make this message anything I want. So what it means is, without knowing the key, I can forge a ciphertext message from one I catch on the wire and create one that will have a block of garbage followed by a 16-byte block of anything I want. And that often is enough. If you consider websites, they often have parameters going along here. You'll have a parameter, you'll have something at the end of this like auth equals 41 and timestamp equals some garbage, and then and action equals deposit and amount equals $100. You'll have strings like that. And often it's the case that there are parameters that don't really matter and you can afford to destroy them, like this timestamp. And there's a really important parameter here you're not supposed to be able to control because they used encryption. And so this ability where I can destroy the timestamp but change this amount can be devastating. And in a lot of systems, it was. Because people, and also there are a bunch of systems that were designed where if you could produce an encrypted message that decrypted it all, it interpreted that as proof that you were the administrator and that you had logged in, because they considered that as proof that you had the secret key. And that's the problem here. You can construct maliciously a message somewhat under your control without knowing the key because of this cipher block chaining. And so there's quite a few more steps, but you do this bit by bit. And there's one that my students struggle greatly with at the end where you actually have to put your name on here, deducing how to forge that message. Anyway, that's a real important attack. And this made people really unhappy with the padding or with the cipher block chaining system. And the current recommended best system is counter mode, where instead of using the output of one block to make the input for the next, you just have a pseudo-random function. It gives you a series of initialization vectors that are applied independently to each block. And the one that's recommended is Galois counter mode, with the Galois function used to create these pseudo-random initialization vectors. That's currently considered the most secure method of AES to be used. Anyway, let me stop this video.